In this video, I'm going to show you how to calculate limits of radical functions using conjugate multiplication. So here we want to compute the limit as x approaches 0 of square root of x plus 1 minus 1, all of that divided by x. Now, of course, the easiest way to compute a limit, if we can, is just to use direct substitution. So why don't we go ahead and try that here. The limit as x approaches 0 of root x plus 1 minus 1 all over x. If we just go ahead and plug in x equals 0, does this come out to a sensible result? Let's see. Square root of 0 plus 1 minus 1 over 0. So square root of 1, then minus 1 over 0, which is just 1 minus 1 over 0, which takes the form 0 over 0. So that is indeterminate form. Alright, so unfortunately direct substitution didn't help us very much. But maybe we can simplify this limit into a form where direct substitution does in fact work. Let's do this in another column here. Now the way we're going to simplify this limit is we're going to multiply by the conjugate, and then we're going to simplify afterwards. So first step, let's go ahead and multiply by the conjugate. So limit as x approaches 0 of root x plus 1 minus 1 over x. We're going to multiply by the conjugate of the numerator with the expression with the root. So the conjugate of this expression, all you have to do is flip the sign of the constant that's outside of the root. So we're multiplying by root x plus 1 and plus 1 instead of minus 1. We'll do that on top and bottom. X plus 1 plus 1. That way we're not changing the value of the limit. And let's go ahead and multiply that out, see what it comes out to. So limit as x approaches 0 of, we've got a fraction. Let's just do the denominator first because that's easy to deal with. That's just x times root x plus 1 and then plus 1. And then how about in the numerator? Well, this is actually just a difference of squares. It's first term minus second term times first term plus second term. So that's just the first term squared, root x plus 1 squared, then minus the second term squared, so minus 1 squared. We can go ahead and simplify this further. So limit as x approaches 0 of, well, root x plus 1 squared, that's just x plus 1. And then we have minus 1 squared, so minus 1. And then that's all over x times root x plus 1 plus 1. Let's keep on simplifying. That's the limit as x approaches 0. This 1 minus 1, that cancels, so we just have x over x times quantity root x plus 1 plus 1. And hey, look, we've got an x on the top and the bottom. We can cancel those out as well. And that just becomes limit as x approaches 0 of 1 over root x plus 1 plus 1. Alright, so now this is in a simpler form. Let's go ahead and try direct substitution again. So we try direct substitution on this limit here. Limit as x approaches 0 of 1 over root x plus 1 plus 1. Just plug in x equals 0 and we get 1 over root of 0 plus 1 plus 1, which becomes 1 over root 1 plus 1, which is just 1 over 1 plus 1, which is just 1 over 2. So there we go, 1 over 2, a half. This is a sensible result for our limit, and we're done. That's the value of the limit, 1/2. Here's another problem. We want to compute the following limit as x approaches -2 of root x plus 6 minus 2 all over x plus 2. Alright, so the first thing we try, of course, will be just direct substitution. So we go ahead and try direct substitution on this limit, plugging in x equals -2. We get root of -2 plus 6, then minus 2 over negative 2 plus 2. Well, let's just go ahead and simplify that. Negative 2 plus 6 is 4, so root 4 minus 2 over negative 2 plus 2 is 0, and root 4 is just 2, so 2 minus 2 over 0, so 0 over 0. And hey, what do you know? That's indeterminate form. So this form doesn't tell us what the value of the limit is, and we have to simplify the limit a little bit so that we can actually get a sensible result. Now, how do we go ahead and simplify the limit? Well, all we have to do is multiply by the conjugate. And then we simplify after that. Alright, so let's go ahead and multiply by the conjugate. So we have limit as x approaches negative 2 of root x plus 6 minus 2 over x plus 2. And then we multiply by that conjugate of the root expression in the numerator here. So still root x plus 6, but flip the sign of this minus 2. It becomes a plus 2 to get the conjugate. So multiplying by root x plus 6 plus 2 on top and bottom. Let's go ahead and see what that is. So let's see. Again, this is just a difference of squares. First term minus second term times first term plus second term. That gives us the first term squared, root x plus 6 squared, and then minus the second term squared, so minus 2 squared. And then in the bottom, we can just keep this as x plus 2 times root x plus 6 plus 2. All right, let's keep on going. So limit as x approaches negative 2. Root x plus 6 squared is just x plus 6, and then minus 2 squared makes minus 4, and then that's all over the same denominator, x plus 2 times root of x plus 6 plus 2. Let's go ahead and keep on simplifying. Limit as x approaches negative 2. The numerator, 6 minus 4 is just 2, so we really have just x plus 2 in the numerator. And then, hey, there's also an x plus 2 in the denominator, so we can go ahead and simplify by canceling these x plus 2's in the numerator and the denominator, and we end up with just limit as x approaches negative 2 of 1 over root x plus 6 plus 2. So now that this limit is simplified a lot, we'll probably have better luck with direct substitution. So try direct substitution for a second time, this time working with the more simplified limit as x approaches negative 2, 1 over root x plus 6 plus 2, and hopefully it'll work out better. So let's go ahead and plug in x equals negative 2, so 1 over root of negative 2 plus 6 plus 2 becomes 1 over root of 4 plus 2. Root of 4 is just 2, so 1 over 2 plus 2, and that comes out to 1/4. Hey, that's a lot better. We get a sensible result this time, so that is the value of the limit. The limit is equal to 1/4. So now we know how to calculate limits of radical functions using conjugate multiplication. And in the future, we'll continue practicing this theme of simplifying limits to a form where direct substitution can actually give a sensible result. In particular, we'll also learn how to do this in the context of trig functions.